Good morning and afternoon, everyone. My name is Emma Cassell, and I'm currently a senior at Quinnipiac University in Hamden, Connecticut. I'm so excited to present my research on the organic matter of the Quinnipiac River Estuary. To begin, I would like to explain that the organic matter of the Quinnipiac River Estuary is of importance to study because of its significance in biogeochemical cycling of the water system. Organic matter is made up of any material that is carbon-based and has a biological origin. It can be allochthonous with origins from outside the system, or it can be produced in the river through primary and secondary production, called autochthonous material. This material can either be part of the dissolved or particulate organic matter fractions I will be discussing. This project as a whole aimed to examine how sources of DOM and POM in the Quinnipiac River change before and after rain events, along with their alteration as they travel downstream towards Long Island Sound. The Quinnipiac River is a prime candidate for study because of its various surrounding terrains. These include coastal, marsh, woodland, and urban areas. Although 9 location sites were sampled 8 times each throughout the summer season of 2019, for simplicity I will focus on 4 sites along the map route. These sites include Lighthouse Point Park at Site 1, Mid-Marsh at Site 4, Quinnipiac River State Park at Site 8, and Fishway at Site 9. To analyze both DOM and BPOM, absorbance and fluorescence measurements were collected. Fluorescence was processed into excitation emission matrices seen in Figure 2, which are contour plots that show peaks of high-intensity fluorescence. We can compare these areas with their corresponding components given in Table 1. For example, peaks B and T correspond to protein-like components. Figure 2 shows an EAM for the most marine site before a rain event, with peak A showing the most fluorescence intensity, which corresponds to terrestrial humic-like matter. Because comparing EAMs directly can be difficult, I compiled the peak results for the 4 sites into bar charts as seen in Figures 3 and 4, and these display the fluorescence intensity differences before and after a rain event between the 4 sites. Overall, all locations demonstrated an increase in fluorescence intensity for CDOM and BPOM before and after the rain event. The Lighthouse site had an overall lower intensity due to the dilution of the terrestrial signal. The most striking difference in these figures is seen between the BPOM of Mid-Marsh before and after the rain event, as peaks B and T show around a 7-fold increase in intensity. Peaks B and T correlate to protein-like components which are indicative of primary production. This will be an interesting site to continue to study in the future to determine its direct effect on the organic matter in the system. To further study this system, we will combine the fluorescence data with stable carbon isotopes to better identify sources of organic matter and estimate organic carbon by measuring carbon concentrations in both fractions. The dissolved carbon concentrations will be used along with salinity measurements to determine if the Quinnipiac River is conservatively or non-conservatively mixed. Together, all of the data will be combined to study the effect of precipitation events and how land use impacts sources of organic matter in the Quinnipiac River Estuary. Thank you so much for watching my presentation.